Hello everybody. So in this video we will discuss a very important phenomena in alternating current chapter, and that is resonance. I'm sure this word resonance is not new to you, and you have learned about the concept of resonance in class 11. All right. Now in this context of LCR series circuit, what is resonance? A series LCR circuit is said to be in resonance condition when the current through it is maximum. Okay, so you'll remember that. Resonance occurs when the current through the LCR circuit is maximum. Okay, all right, now we already have the expression for the EMF that we obtained. Okay, the amplitude of EMF is given by E naught is equal to I naught R square plus XL minus XC whole thing square under root. This expression we already obtained in the previous video. So from here, what will be the current amplitude? Current amplitude will be I naught is equal to E naught divided by this term in the square root. And we know very well this term in the square root, what is it called? This is called the impedance. Okay, so basically divided by the impedance. All right, so let's call this equation 1. Okay, now look at equation 1 and tell me, when will this current be maximum? So this current will be maximum if the denominator is minimum, yes or no? And this denominator is minimum if this part, the part in the bracket, is equal to 0. All right, so here from equation 1, I will be maximum if what? If XL minus XC is equal to 0. This term is not there. L is equal to XC. Therefore, impedance is Z is equal to R square plus XL minus XC whole thing square under a root. Now since this term is not there, you will get R square under root, so that is equal to R. So you can see here that the impedance is contributed by the resistance only. Okay, so it also means here that the circuit is a purely resistive circuit. Resonant frequency. The frequency at which the current amplitude I naught attains a peak value is called natural or resonant frequency of the LCR circuit and is denoted by FR. So we have seen that at resonance, the condition is XL is equal to XC. This is the resonance condition. XL, we know it is omega L. XC is 1 by omega C. So you have omega square is equal to 1 by LC, or omega is equal to 1 by root LC. But we know that omega is 2 pi F. Okay, 1 by root LC. Now since this is the resonant frequency, I'm going to put a subscript here R, just to indicate that it is the frequency at resonance. So therefore FR is equal to 1 by 2 pi root LC. This is the expression for the resonant frequency. So some of the important characteristics of the series resonant circuit are given here. Number one, at resonance, XL is equal to XC. That I've told you that it is the condition for resonance. And number two, also we have found resonant frequency. We have found it to be this much, or is given by this expression. The impedance is purely resistive. All right. Why? Since the impedance is found to be equal to the resistance R. So what does this mean? The impedance is purely resistive. It means that the effect of the capacitor and the effect of the inductor is negligible. Only the resistance play the most dominant role. Is it clear? So we can also say that the circuit is a purely resistive circuit. The current has a maximum value of E naught by R at resonance, and the current is in phase with the voltage. This we know from the phasor diagram of a purely resistive circuit. So you can see in this phasor diagram that E naught and I naught, there is no angle between them. The phase difference between them is 0. So in that case, we say that they are in phase. All right, so these are the important points when it comes to resonance of LCR circuit. Resonance curve. It is a graph showing the variation of current with frequency. So in this diagram, you have seen that I have plotted two graphs. The current is taken along the y-axis, whereas the frequency along the x-axis. So this curve here and the other one, these are called the resonance curves. All right. So you can see here that this curve here has a large peak current out here. So the current is large. Why? Because this is due to this is the curve for low value of R. Okay. And here the peak value of the current is small. Why? Because this is the curve for high value of R. Is that clear here? Now, what do we mean by sharpness of resonance curve? Let us have a look at the resonance curve once again. So you can see here, this resonance curve is quite sharp like this, whereas this one is a little bit flat. Let me draw one more just for the sake of understanding. So let's say I have another curve like this. Okay, let me take a white color. So we have one more curve, something like this. All right, so you can see here that this curve, the third one, is even more flatter. Okay, so why? Because this has the highest value of R compared to the 3. Highest compared to the other two, highest value of R. You understand? So the more the curve rises like this, it means that it is sharper. So from here, the lower the value of R, the more sharp will be the curve. Okay, and the sharpness of this curve is determined by a coefficient called the quality factor or the Q factor. So let us have a look. What is this quality factor or the Q factor? The Q factor of a series resonance circuit is defined as the ratio of the resonant frequency to the difference in two frequencies taken on both sides of the resonant frequency, such that at each frequency the current amplitude becomes 1 by root 2 times the value at resonant frequency. Now have a look at this graph out here. So this peak value of current is denoted by I naught. And what is the frequency that gives the value of I naught? That frequency is omega R, which is the resonant frequency. Yes, we have said that resonance is a condition where the current is maximum, right? So here, and that frequency where current is maximum, that is called resonant frequency. Okay, now what we do is we take a value I naught by 2. Let's say this is the point where I naught by root 2 is. And then we draw a line. This line intersects the graph at 2 points, this point and this point. So this point correspond to omega 1 and this point correspond to omega 2. So obviously omega 1 and omega 2 are the two frequencies at both sides of omega r, where the value of current is 1 by root 2 times the peak value of the current. Is this clear here? So that ratio of omega r and minus omega 2 minus omega 1, that is the Q factor, right? So that is Q here is equal to what? Ratio of the frequency at ratio of the resonant frequency 2 divided by the difference between omega 2 and omega 1. So this will be omega 2 minus omega 1. Okay, so this is resonant frequency, and this value omega 2 minus omega 1, it has a name. And what is the name of this? This is called bandwidth. Is that clear here? So that's one way to define the Q factor. There's another way to define the Q factor. Let us see how. The Q factor may also be defined as the ratio of the potential drop across L or C to the potential drop across R. That is, Q is equal to VL, or you can write VC by VR. Okay, let us stick with this. VL is actually I naught XL, and VR is I naught X, not XR, sorry, I naught R. So this and this will be cancelled. And what is the value of XL? XL is omega L by R, right? And what is the value of omega? We already found the value of omega. You remember omega, how is it written? Omega is 1 by, let me use a different color so that you will not get mixed up. Let's take red. Omega is 1 by root LC. Let us make use of this. Okay, so instead of omega, I can write, let me take L by R in front. Then this will be 1 by root LC. So I can do one thing. I can write like this, L square, right? By R root LC. No. Then instead of writing these two square roots like this, I can just write a single square root. Like that, right? So 1L and 1L will be cancelled. So you get 1 by R root L by C. So that's another expression for the Q factor of the series LCR circuit.